We distributed a draft of the lecture notes to send to you. We already received some feedback from one of you, which I found very, very useful. So I'm going to change the lecture notes, this chapter, and send you a new version. I would very much appreciate any comments at any time. You did not receive it? Did? Okay. The topic of today's talk, we continue with the standard rate model. And we used two formulations which are very similar. One was tau ri dot is equal to minus ri plus a sigmoidal function of hi, where hi is sum over j of jij rj, sum of the activities of all neurons in the network weighted by the corresponding synaptic efficacy and some external input. This was one formulation that we used. And another one was to consider the dynamics. I can't remember whether I used V or H. I'm going to use H because that's what we have in the notes. Plus sum over j of jij rj, where ri is a non-linear function of hi. When I was not, I said something that was not exactly true. Well, it was not true at all last week. These two formulations are lead to the same trajectory when the external inputs are constant in time. When they do change in time, one can find a corresponding input that will move you from one formulation to the other. So our goal today will be to study this formulation, study the dynamics. I can't remember where I stopped last time. Can you remind me? Did I go beyond this, or this was the last thing that I did last week? The equivalence. Okay. So what we will do today is we will consider these equations, and we will study how the synaptic connectivity affects the dynamics, how this matrix jij affects the dynamics of this network. But we will start with simple examples and make and keep on complicating the problem. So the simplest example would be that all synapses are equal to 0, an isolated neuron. So this is called example 1. So if all synapses are equal to 0, then basically we're interested in dynamics that looks something like this. Tau h dot is equal to minus h plus h0. This is a simple differential equation. It has a closed form solution, which is h of t is equal to h0 e to the minus t over tau plus 1 over tau integral to time t, external input e to the minus t prime over tau dt prime. So this is a solution to this equation. So depending on the dynamics of external input, the dynamics of external input will determine this h, or this measure of activity of the neuron. And I guess that you already know that if the external input is constant, then h of t is equal to a decay of the initial condition. This is the decay term plus h0. So basically the dynamics will converge to h0 with a time constant tau. So if we just plot it, so let's assume that the initial condition is 0, then the dynamics will look something like this. Or like this. Depending on what? Depending on the value of tau. So this would correspond to short tau, small tau. This would correspond to a large tau. And what's the value that the network or the dynamics will reach after 1 tau? Something like 63%. This is just 1 minus 1 over e. 63%. So the time it takes the dynamics to reach this saturation value corresponds to the time constant of the neuron. Another way of thinking about it, this is actually important from a computational point of view, thinking about the brain. So what's the tau of the brain, in the brain? What's the corresponding tau of neurons? Let's say 10 milliseconds, maybe 20, maybe 50. How long is a sentence? A sentence. I'm saying a sentence. How long is it? I'm sorry? Maybe if you, well, depending. There are short sentences and long sentences. And sentences are processed in the brain, right? With neurons. So if sentences take a few seconds, or maybe 1 second. Long sentences take maybe a few seconds to process. They are processed by elements whose characteristic time scale is maybe 10 milliseconds. In order to understand the sentence, we need to memorize things about 2 orders of magnitude, for 2 orders of magnitude longer periods of time than the characteristic time of the system. So each neuron forgets the input within 10, 20 milliseconds. It's no longer influenced by the history after several tens of milliseconds. Nevertheless, we are able to process things in timescales that are much longer. So what's the solution? How will the network solve this problem? So one way in which this can be solved is by recurrent dynamics, which can increase the effective time scale of the system. So this is already an important statement. If what you're saying is right, then this implies that recurrent dynamics is something that is necessary for even simple things like memorize for memory of things for seconds. Okay, let's bear this question in mind and bear your solution in mind, and we'll get back to it. Questions? Let's do another example. This was perhaps too easy. So the second example is called the OTAP. So in this case, we were thinking about a neuron in which we inject current to the neuron and look at the dynamics of, let's say, the firing rate or the memory potential. The OTAP is what is arguably the simplest network possible. So you have one neuron, and it innervates itself. So looking at the dynamical equation, they look something like this. That would be tau h dot is equal to minus h. You can omit the index for the time being, plus j times the activity of firing rate of the neuron, which is r, plus external input. So in the literature, the OTAP is used as a toy model for things like working memory, exactly what you were talking about. And there's some argument. There has been some argument whether OTAPs exist at all, whether one finds in the brain neurons that innervate themselves. The answer is yes, but. I think that there is evidence for existence of OTAPs, but it doesn't seem to be very important. The reason that it's not important is that each neuron in the brain receives, or in the cortex, receives input from how many neurons? Maybe 10,000, maybe a few thousand. So we don't care about 1 out of 1,000 or 1 out of 10,000. But still, this is a useful model, at least as an introductory model to understand the standard rate model. So what is the solution to this differential equation? What's the solution to this differential equation? So there's no analytical, in general, there's no analytical solution, closed form solution to this equation. So now we have, we can do one of two things. One possibility is retire, say, okay, whatever, let's just solve things analytically, and and find closed form, so only look for things that have a closed form solution, or start using tools from nonlinear dynamics to analyze this equation. So what's the first thing that's worthwhile doing? When we have a differential equation and we want to understand the dynamics, we cannot just solve it. What do? Look for fixed points. Okay, so we look for fixed points. So what are fixed points? Fixed points, as all of you that took Lawton's course know, and those that didn't take Lawton's course will know now, fixed points are the solutions to the equation h dot is equal to 0. In this case, it will be h is equal to j times r plus h 0. We can replace r with g of h. So how the solutions of this equation look like? Let's say that g of h looks something like this. This would be g of h. This would be h. Let's say, I don't know, something like this. How are we going to find the fixed point solution? Okay, so when j is equal to 0, then h is equal to h0. That's the solution. That's easy. But what about the case when j is not equal to 0? We'll consider positive sinuses, excitatory sinuses. So typically, we denote the fixed point solution with a star. So the fixed point solution will have the form h star is equal to j of gh star plus h0. So we are looking for values of h such that the left-hand side is equal to the right-hand side of the equation. Let's consider the case of h0 is equal to 0 for simplicity. So we're looking for solution to the equation h star is equal to j g of h star. So looking at it geometrically, we can go over all possible values of h star and look for intersection between the left-hand side and the right-hand side of the equation. So the left-hand side of the equation is just the identity line. So we'll plot the identity line. The right-hand side of the equation is this red line. And the intersection line is this point. The point where the red and blue lines intersect. So that's a fixed point. How will this fixed point depend on the value of j? What will j do? The slope of well, sigmoid has many slopes. I mean, where? Well, basically, what j will do is we'll scale up the sigmoidal function. So if we take a small value of j, this would be like multiplying the sigmoidal with a small number. If we take a large value of j, then this would correspond to scaling up this sigmoidal function. So if j, so let me draw it here.
So why not just move j to the left-hand side?
Move j
To the left-hand side. It's easy to see the slope of the straight line.
So the possibility would be to divide, to move j to the other side and then look at the intersection. Okay, let's do it like this. Let's try and make a better drawing. Now we can consider, so this would be now g of h star, the function of h star. Now we should consider different slopes of the left-hand side value. So our equation now is, we're thinking about the fixed point equation h star 1 over j h star is equal to gh star. That's your suggestion, right? Okay. So how will this look like when j is very small? When j is very small, then this would be the left-hand side for j, which is very small. This would be the behavior when j is very small. What will happen when j is very large? Well, when j is very large, it will look something like this. So the fixed point solution when j is large would be this one. And for an intermediate value of j, there can be a situation where we have multiple fixed points. This would be one fixed point, this would be another fixed point, and this would be a third fixed point. So one thing that we already gained from the OTAPs is a possibility of multiple fixed points. This is something that did not exist in the isolated, in the neuron that is without any synapses. Okay, so we found the fixed points. What's the next step? Classify them. What do you mean by classify them? Stability. Analyze the stability of the fixed points. So how are we going to do that? How are we going to analyze the stability of the fixed points?
Simply look at the portrait.
I'm sorry?
Simply by looking at the portrait. So we can move it this way and see whether the points moves. I don't know about this one.
The derivative is positive or negative on other coordinates.
The derivative of what?
The h.
H dot. Okay. So in order to analyze the stability, so we need to plot h dot as h dot is a function of h.
because in this situation, in this case, we don't need to actually plot this because the one function is on a straight line, so you can rotate it, and it's just like when you analyze the 1D system.
I'm not sure that I understand what you mean by rotate.
Yeah, so because the left side is a straight line, so you can just simply imagine it's a 1D system, so it's like move your head this way and.
Well, it is 1D system, and in fact, what we do will be, if this is what you meant, we will subtract.
Yes.
We'll subtract the g function from the identity line, or more precisely, we need to subtract g of h from subtract h from g of h. We cannot exactly do it here because what we changed was not the jg, but we change the slope.
Yeah,
but we can multiply it by, I mean, we can think about the dynamics multiplied by j, and then we can do this subtraction. So what can we say about the case where we have this fixed point below? How will this look like? So consider this case, a case that we have just one fixed point here. So in this case, so we know that at the fixed point, that's the value of the fixed point. This would be the case of j that is small. So this is the fixed point. So at the fixed point, we know that h dot is equal to 0. For values that are of h that are left of the fixed point, smaller than the fixed point, what will be the value of h dot? What will be the value of h dot?
So which minus?
It will be dominated by this term, which decreases very quickly. The minus h decreases very quickly, so it will be positive here. And above the fixed point, it will be negative. So the dynamics will look something like this. So for small values of h, the dynamics will be in this direction, and for large values of h, it will be in this direction, implying that this fixed point is a stable fixed point. What about this case? What about the case in which j is very large? So in this case, the fixed point is at here. So the value h dot is equal to 0 at this point. So what can we say in this case?
It's the same.
The same. The slope of this line at the fixed point is larger than the slope of the sigmoidal function. So the stability or will be dominated by this identity line, and again, this fixed point will be stable. What about the intermediate case?
Two stable,
J that is not very large and not very small. So first we know that there are 3 fixed points. There will be 3 fixed points. And for this fixed point, the situation is like this situation. For this fixed point, the situation is like this fixed point. So it will look something like this. But we'll have the opposite for this fixed point. So h dot will look something like this. implying that this fixed point is stable, this fixed point is stable, whereas the intermediate fixed point is unstable.
So what I suggest is just you theta you had is exactly the same.
Okay. So that's one way of analyzing fixed points, which is useful. I know that those of you that took Lotem's course, you already know these things, but I guess that not all people here took Lotem's course, so I'm doing it slowly. So this is one way of analyzing the stability of a fixed point. So there's a more formal way of analyzing the stability of the fixed point, which is what? How do we do it? This is using Taylor expansion. So Taylor expanding the fixed point around, Taylor expanding the dynamics around the fixed point. So let's do it. So the idea is that we can consider small perturbations around the fixed point. We can consider small perturbations around the fixed point and look at the dynamics close to the fixed point. So we take this and we plug it into our differential equation. So tau h dot, instead of h, we write h star plus delta h, where h star is the fixed point, is equal to minus h, which is minus h star plus delta h, plus j g h star plus delta h plus h0. What do we do with this term? So h star is a constant. This is just the value of h at a fixed point. So the only dynamic variable is the perturbation, is delta h. So you can say that tau delta h dot is equal to minus h star, this is this term. What can we do with this second term? What can we say about g of h star plus delta h? If delta h is small? Take delta h, let's see if delta h is small. So what do we do? Sorry? Why should we? I mean, what do we do with this term? Assuming that delta h is small, we can Taylor expand it. So we Taylor expand it. So this will be asymptotically true. So the zeroth term order will be j g h star plus j plus h0, and we have first order terms, which will be this term minus delta h plus j g prime h star times delta h. So this was just Taylor expanding this equation and taking only first order terms, taking only first order terms with respect to delta h. What can we do with this term, the zeroth order term? What do we know about it? It's equal to? Why is it equal to 0? This is just a fixed point equation. This is a fixed point equation. So this is equal to 0. So we are left with the dynamics tau delta H dot is equal to minus delta H plus J G prime H star is equal to minus minus 1 minus J G prime H star times delta H. So now we should be happy, relatively happy, as happy as one can be in this class. The reason why we should be happy is because this is a linear equation, linear differential equation. We know how to solve it. So I will denote this term by lambda, and then the dynamics is just delta H of t is equal to delta H times 0 times e to the minus lambda t over tau. The implications are that if lambda is positive, then any perturbation will converge to 0. On the other hand, if lambda is negative, then any perturbation will diverge. This implies that this fixed point, if lambda is positive, then this fixed point, the fixed point will be stable. If lambda is negative, the fixed point is unstable. Any questions? So what determines the stability of the fixed point according to this framework? This would be just the sign of this term. G prime of H star is the slope of the function at the fixed point. So going back to this drawing, if this slope is larger than 1 over j, what will happen to the fixed point? If the slope of g at the fixed point is larger than 1 over j, what will be the sign of lambda? The sign will be negative, and the fixed point will be unstable, like this one here. This is a slope here. The slope is above the identity line, or the slope is above 1 over j. Whereas, if the slope is smaller than that value, like we have here or here or here, then the fixed point will be stable. So that's an alternative way, perhaps a more formal way, using Taylor expansion to analyze the stability of a fixed point. Questions? So one thing that we gained from this example is an understanding that there exist some values of j such that the dynamics is bistable. The dynamics is characterized by two stable states, this one and this one. So if the dynamics is bistable, what can we say about the ability of this very simple network to store memories? In the regime where the dynamics are bistable, what can we say about the ability of the network to store memories? So we started by discussing a problem. I'm saying a sentence, and by the end of it, you should have forgotten the beginning. So comprehension, it's impossible. Well, maybe it's impossible. But if the dynamics are bistable, what are the implications? The implications are that if we start from initial conditions that are high, then the dynamics will converge to this fixed point. If we start with initial conditions that are low value of h, the dynamics will converge to this fixed point. So in principle, despite the fact that the characteristic time scale of the network is tau, the network can remember things about the initial conditions for how long? Forever. So we gain an ability to store memories forever just by introducing the OTAP, just by introducing self-coupling. What is the price that we pay? The ability to store memories is limited to one bit of information. You can only remember that the initial conditions were high or low. There are no intermediate values. So this is a way of storing memories. Note that it's a digital way of storing memories, one bit. And the necessary conditions are that we'll have something like a positive feedback. This is a self-coupling, and saturation. The fact that the G function saturates. So all memory devices, including the ones on your cell phone, are constructed this way. Positive feedback and saturation. These are the basic ingredients of a memory. Questions? Yes?
If we get 4 stable points?
Here? The easy answer is no. But why 4? Why did you say 4 and not 5?
Well, the one in the middle is not stable.
Okay. Why 4? I mean, why? I mean, why is your question about 4 and not 20
well,
or?
Now you stated that basically there are 2 stable points.
There can be 2 stable points. Yeah, the two extreme points. Why is your question focused on the number 4?
Maybe I missed something. But, it seemed like we found 4 stable points.
What are the 4? Oh, I understand your question. I think that I understand your question. So the value of the fixed point will be determined by J. So in principle, you can have an infinite number of fixed points, each one characterized by a different J. The interesting result here is that for a given J, you have there is a regime in which you have 2 stable fixed points and 1 unstable fixed point. But you can for a given J for sigmoidal function. Those that studied bifurcation, nonlinear dynamics, what's the bifurcation that brings you here from 1 to 3? Cell node bifurcation. So this curve moves up and down. These two stable, this stable and unstable fixed points meet and disappear. This is a saddle node. This is known as a saddle node bifurcation. Good. Okay. Enough with a single neuron. Let's talk about a network. So the next example that we're going to consider is a case where all neurons are connected to all neurons. But to make our lives easier, we assume that the strength of all connections is the same. So let's write the equations. Oh, I think it's a good time to take a break. Sorry.
שאלה הזו מתקדמת לשאלה הפונקציונלית. תיקחת בשעתו, כי אנחנו שנה ג' בתואר ראשון. והיה כתוב רק על השיעור הזה. אז רק פספסנו... רק כתוב שזה השיעור הראשון.
פספסתי את השיעור הראשון.
שהיה שיעור דבר בדיוק?
ביום ראשון, 4 שעות.
האמת שאני ראיתי את זה.
זה בשנתון זה לא היה? אוקיי, לא ראיתי את זה בשנתון. טוב, אני פגשתי, רק פספסתי. השאלה הפונקציונלית, יש את המצב שבו הכלי ממשיך, ואז יש לנו נקודה יציבה ונקודה לא יציבה. לא, יש לנו את הנקודה יציבה כאן, את הנקודה לא יציבה
אורג'ינלית.
כן, אבל אז יש לנו, אם הסיגמנט שלנו הולך טיפה למעלה, כאילו פעם מבינים אותו, אז יש לנו באופן אינטרנציונלי נקודה לא יציבה ויציבה אחת ממש קרוב לשנייה. זאת אומרת, אנחנו מתכנסים תמיד לנקודה יציבה?
יש לנו 2.
כן, זאת נשארת, ויש לנו, זה עדיין יש לנו 3, אז יש לי באופן אינטרנציונלי כל כך קרוב, זה לא מפריע לנו פשוט להתכנס תמיד לנקודה יציבה?
שואל שאלה על הגבול. מה שיקרה זה שיהיה לך, מציירים את H דוט כפונקציה של H, תהיה לך נקודה אחת יציבה כאן. אז נתחיל, לפני כן יש לך נקודה אחת יציבה ונקודה אחת לא יציבה. דינמיקה נראית ככה. נציג אותה שנוכל לצייר. אוקיי? כשהנקודות האלה מתקרבות, אז המרחק הזה הולך וקטן. בסוף אתה מקבל נקודה שהדינמיקה נראית ככה. יש נקודה, היא הולכת לכאן, היא הולכת לכאן. כאן הדינמיקה, הזמן שלה הולך לאפס. המהירות הולכת לאפס. אתה תעשה שינוי קטן, זה תיעלם. אבל זה לא נורא...
כי זה נהיה מבחינה טבעית?
בכל עולם שיש בו קצת רעש, אז או שיש לך 2 נקודות, או שיש לך... או שהדינמיקה תתחיל כאן, תהיה מהירה, תהיה מאוד מאוד איטית, ואז תחזור לאפס. זה מה שיקרה. כן.
אני ראיתי את השיעור ביום ראשון, יש לי שיעור שמתנגש. אוקיי, האם אתה חושב שאפשר להיעזר
אתה יכול להיעזר, אני לא יכול להבטיח שיהיו סיכומים.
הבנתי שיש סיכומים שנמשכו
זה בערך אותו דבר. אני גם כותב ספר קורס. אני מקווה לחלק אותו as we go. זה יותר טוב. אבל אני לא יכול להתחייב. אני עובד על זה קשה.
לא ברמת ההתחייב, ברמת ההתחייבות. נגיד, מתי החלטות עולות, כמה אתה חושב
בדרך כלל ניסיון העבר זה שהן עולות לוקח זמן. שבועיים. אפשר לבנות את זה. סיכומים, אני מתכוון לתת בסוף כל פרק. לא בסוף כל שיעור, בסוף כל פרק. נגיד, הפרק הראשון, השיעור הראשון היה introduction כזה. הכל ניקח שבועיים. גמר הפרק. אי אפשר לבנות על זה, אבל אפשר לקוות.
אוקיי, טוב.
כבר דבר חשוב.
שנתון שלנו שונה? אוקיי, סבבה. לא, זה שיהיה דברים מסובכים. זה שיהיה דברים יותר מסובכים. מדי טריוויאלי כזה, לפחות יש לנו משהו כן לפתור.
כן.
השאלה אם זה נותן משהו מעבר למודל הטריוויאלי.
זה דברים שאתה יכול לעשות, אתה יכול לקחת נגיד step function, אז יותר ברור בדיוק לעשות k עם j, אתה יכול לקחת expressive linear 0, אז זה ערך מסוים.
ואז עולה עם מדרגה לינארית.
אז אפשר לעשות כל מיני דברים.
כן, כן. כן, השאלה אם זה נותן איזה אינסייט מעניין על A,
זה נותן אינסייט יותר מעניין מהפרובלם.
כן.
יודע אם הוא בסדר. לא יודע אם הוא בסדר. איפה כיף?
I'd like to start. So some apologies. So last week we overlapped a lot with what you did in, or what LSEC students did in Bal's course. Today there will be some overlap, substantial overlap with Lotem's course, and I promise that soon we will take off and do things that are perhaps newer. You don't? Okay, if there are no objections, we can just do Lotem's course. Okay, so we're talking about all-to-all connectivity. And we will assume that for all neurons receive exactly the same input. This is the model that we will consider. So now the equations are tau hi dot, it's still written, doesn't matter. Tau hi dot is equal to minus hi plus sum over j of jij rj plus hi0, which will be equal to minus hi plus all jij's are equal to j, so it's equal to j sum over j of rj, which is g hj plus h0. So this is slightly more challenging than the OTAPS example. How do we solve these equations? Well, as before, we cannot solve them. We cannot come up with a closed form solution, so we need to start analyzing the equations in the tools that we have, which are basically looking for fixed points and studying their stability. So what are the fixed points of this set of equations? We have n such equations, one for every neuron in the network. Well, we don't know that you cannot, not necessarily. I mean, if you put here 0, that's not necessarily true that this is equal to minus this. So the fixed point, at the fixed point, we know that hi dot is equal to 0 for all neurons. So this would imply that hi star is equal to sum over j. Is equal to j sum over j g of hj star plus h0. Right, that's a fixed point solution. what can we say about the values of h at the fixed point? So this sum is sum over what? Sum over all neurons in the network. So note that at a fixed point, the fixed point solution for each neuron is independent of its identity. And in fact, this is not surprising because all neurons receive exactly the same connectivity because of the symmetry of the network. So we know that hi star is equal to h star. The fixed point solution is equal for all neurons in the network. This is because this sum is identical for all neurons in the network. It does not contain the identity I, the index I. So we know that h star is equal to j sum over j of g h star plus h0. But note that this sum contains elements that are all the same, all identical. So h star is equal to j times n g h star plus h0. So this is nice because we are back to the OTAP solution. With one difference, j is multiplied by n. So one thing that we learned about the OTAPs is that the interesting regime is a regime in which the value of j is intermediate. If the value of j is equal to 0, then we have one solution. If the value of j is very large, we also have one fixed point solution. The interesting regime in the OTAPs was j, which was like order 1. Now in this problem, if we think about a large network in which n is large, then independently of the value of j, we are in the boring regime where all neurons are at the saturation value. This is one reason why we often, when considering large networks, we often scale j like 1 over n. Not always, but often. We will also consider other scalings of the strength of connectivity. But if the scaling is 1 over n, then this sum will be order 1. This sum will be kept order 1 even when the network is large. Okay, so we know something about the fixed point solutions. We've already analyzed it in the case of the OTAP. What is the next step? What should we do next? We have the fixed points. Stability. So how are we going to analyze the stability? Well, now I cannot do it because you have here n differential equations, and I cannot draw things in n dimensions unless n is 1, n is equal to 1. So we also learned another technique, which is to use a Taylor expansion to analyze the stability of fixed point. So let's use this technique. So again, we consider small perturbations around the fixed point solution and look at the dynamics of these perturbations. But now, unlike the previous case, a perturbation is a vector, not a scalar as before. So we assume that the norm of this vector is small. We have the fixed point solution. I will use this arrow to notate clarify that we're talking about vectors. So we consider small perturbations around the fixed point, where this notation implies that let's use different notation. So we have H star. This is a scalar times a one vector plus a small perturbation. And now we can apply exactly the same trick as before and look at the dynamics of the perturbation. So tau H star plus delta Hi dot is equal to minus H star plus delta Hi plus sum over J of G of H star plus delta Hj plus external input. So now we have a set of n differential equations. And as before, we will Taylor expand these equations. So the derivative of H star is equal to 0. So we are left with tau delta Hi dot is equal to minus H star, this is this term, plus sum over J G H star plus H0. This is a 0th order expansion of the right-hand side of the equation around around H star, around the fixed point. Now we take the first order terms, which would be minus delta Hi. We have a J, should be a J here, plus J sum over J, the derivative of G at a fixed point, times delta Hj. Sorry?
Because you added the J. Negative H star plus J.
So as before, this is a fixed point equation. So this is equal to 0. And this is, and here we only have linear elements in delta H. So we can use matrix notation. So the derivative of the vector delta H is equal to minus delta H vector I want to be consistent, equal to a matrix M times delta H, where the M matrix is composed of two elements. This is the first contribution, which will in matrix in vector notation will be what? The first term. Unity. Or identity. Okay, plus J. What can we say about this element? What will be the contribution of this element in matrix notation? So for every element I, we have a contribution, an equal contribution from every element J. Sorry? No. It cannot be a vector because it has to be a matrix. What would be the matrix? How would it look like? So we have this constant term, J times G prime H star. I'm sorry? No. If we have the identity matrix, we will not have crosstalk between J and I. Ones. A matrix that looks like this. Matrix which is all ones. It's not identity matrix. Another way of writing this matrix would be it's equal to minus the identity matrix plus J G prime of H star times 1, the vector 1 times 1 transpose. So a column times row vector in which all elements are equal to 1. Okay. So now I'm going again to do a small detour that will not be very interesting to those that took Lotem's course. Nevertheless, it's worthwhile for those who haven't. So how are we going to solve this equation, or this set of linear differential equations? So the difficulty here is that the dynamics of one neuron depends on the dynamics on the values of other neurons. This is different from this case in which we had one neuron dependent only on itself. So what we look for is a representation of the problem in which we can write this set of differential equations using modes which are independent from each other. This is what we need to do. And doing it is actually pretty straightforward. And I will do it here. So the general problem that we need to solve is this set of differential equations. V dot is equal to mv, where v is a vector and m is an n by n matrix. And we will assume that m is diagonizable over C. So this means that there is we can write there exists a matrix U such that U minus 1 M U is equal to lambda, where lambda is a diagonal matrix. What can we say about this U? Let's talk about the columns of U. What's special about the columns of U? There are eigenvectors of M. Why? How do you prove it? So columns of U are eigenvectors of M. The way to see it is to multiply it by U. So you multiply both sides from the left by U, and then we're left with the equation mu is equal to U times lambda, and because lambda is diagonal, this is equal to lambda U. Okay. Or more precisely, we should say that columns of U are right eigenvectors of M. What can we say about U to about U to the minus 1? How is U to the minus 1 related to the eigenvectors of M? What can we say about the rows of U to the minus 1? I'm sorry? Which eigenvectors? Left eigenvectors. How do we prove it? We multiply the equation by U to the minus 1 from the right. And then we get U to the minus 1 M is equal to lambda U to the minus 1, which is equal to U to the minus 1 times lambda, because lambda is diagonal. So the rows of u minus 1 are left eigenvectors of M. So let's denote these right eigenvectors of M by ui, and denote the left eigenvectors by wi, and this also implies that w t I times uj is equal to delta ij. This is because u minus 1 times u is equal to the identity matrix. Okay, but these are all properties of things that you all know from linear algebra. This is a problem that we need to solve. So how are we going to solve it? So the way to solve it is to decompose V using the eigenvectors of M. So I'm going to decompose V using the right eigenvectors of M. So the next step is to take the derivative of V. So V dot is equal to sum over j aj dot uj. But this is also equal to M times sum over j aj uj. Oh, sorry. Which is equal to sum over j aj lambda j uj. This is because M times uj is equal to lambda j uj. Why is this helpful? So we know that sum over j of aj uj is equal to sum over j aj lambda j, sorry, is equal to aj lambda j uj. So this is this equation where we decomposed V using the right eigenvectors of the matrix M. What would be the next step? What should be the next step? The next step is to multiply this equation from the left by the left eigenvectors of the matrix M. So let's multiply it from the left by W transpose K. What can we say about W transpose K times Uj? This would be equal to delta Kj. So, considering this sum, the only element that will contribute anything would be the kth element. So the left-hand side of the equation becomes what? AK dot. Because from this sum, the only element that contributes is the kth element. All other elements don't contribute anything because of this identity. What about the right-hand side of the equation? So we are left with AK lambda K. Now we can do it for all k's. We should do it for all k's. So rather than having these n differential equations for the different neurons, now we have n differential equations, these differential equations, for the different modes, the different projections on the eigenvectors of the matrix M. But these modes are independent of each other. So these become scalar equations which we already know how to solve. So what's the solution? This equation. And I think that I lost, no, I didn't lose tau here because there was no tau. Good. So now we know how to solve a set of differential equations, linear differential equations, using this method. So we can apply this method to our network. So this is the problem that we're interested in. Tau h dot is equal to m, tau delta h dot is equal to m delta h, where this is our M matrix. So what are the conditions for stability of the fixed points? Didn't you do it with Lotem? No? Okay. I'm sorry? Can you say it again, please? Okay. But before that, what are the conditions for the stability in general of this equation? So we'll care about, well, we'll have a set of equations that will look like this. And where these are the eigenvalues of M. So we care about the sign of these eigenvalues, and the fixed point will be stable if the sign of the eigenvalues is negative, or more precisely, it will be unstable if at least one, if the sign of at least one eigenvalue is positive. What will happen if the eigenvalue is equal to 0? What can we say about that? We don't know. So if the eigenvalues are when we diagonalize around the fixed point, if the eigenvalue is if one of the eigenvalues is equal to 0, this is a direction in which implies that, well, we don't know. We need to take higher order terms in our Taylor expansion in order to address this question. But the fixed point will be stable if all eigenvalues are negative. So now we have this matrix, which we need to find the eigenvalues of this matrix. So what can we say about the eigenvalues of this matrix? So the question of stability of the fixed point of the network depends on the eigenvalues of this matrix. So the next step is to try and figure out what are the eigenvalues of this matrix. How are we going to do that? So this matrix is composed of a sum of two matrices, minus the identity matrix plus another matrix. So this is easier, right? What are the eigenvalues of the identity matrix? And what are the eigenvectors? I'm sorry? This would be the eigenvector of the matrix. I just didn't understand your... Yeah? So what are the eigenvectors of an identity matrix? Any vector is eigenvector of the identity matrix, including the one that you proposed, but any vector is eigenvector of this matrix. So if we care about the eigenvectors, well, one way of finding the eigenvalues is to find the eigenvectors, and well, we know what the eigenvectors this one are. Any vector is an eigenvector. So we are left only with trying to figure out the eigenvectors of this matrix. So this matrix has a peculiar form, right? It's a constant times the product of a vector with its transpose. So what are the eigenvectors of this one? Well, what are the eigenvectors in the first place? Let's try and think. What do they mean? So eigenvectors are modes. You can think about them as some modes or directions in which the modes are independent of the matrix. So what can we say about the symmetry of this problem and the symmetry of this matrix? It's symmetric in what sense? All the components are the same. So what kind of eigenvectors should we consider? Sorry? Equal. So let's think about an equal eigenvector. So what would be an equal vector? What do we mean by an equal vector? Vector in which all elements are identical. So if we multiply this by the one vector, what do we get? So this would give us n, and then we're left with this vector. In fact, one eigenvector of any matrix that has the form U transposed is U. I leave it to you to prove it. Specifically in this case, one eigenvector is the homogeneous, it's called the homogeneous eigenvector in which all elements are equal to 1. So this is one eigenvector. What will be the eigenvalue associated with this eigenvector? So let's see. So we have m times 1 is equal to minus I plus j g prime h star 1 transposed times 1 minus I times 1 is equal to minus I times 1 is equal to 1 or minus 1. And here we have plus j g prime h star. 1 transposed 1 is equal to n. This is sum of n elements. Each one is equal to 1 squared times 1. So this is equal to minus 1 plus j g prime h star n times 1. So what is the eigenvalue? This is the eigenvalue. This is what we had for the OTAPs. This is what we have here. What's the difference? The value of n. The value of n. So we had here minus term. So the value of n, the fact that we have n here. So this is the first perturbation that we consider, the homogeneous direction, that all neurons change as one. And there we find that the same conditions for stability that we had for the OTAPs hold, except for the fact that rather than having j here, we have j times n. And if we use proper scaling where j is equal to 1 to some number times 1 over n, the problem will become identical. So this is the first eigenvector, and now we computed the eigenvalue. What about the other eigenvectors and eigenvalues? This was 1. We have n minus 1 left. What can we say about the n minus 1 other eigenvectors and eigenvalues for this matrix? I'm sorry? Orthogonal to what? They're orthogonal to each other. This will be true in general for symmetrical matrices, and specifically for this matrix, but you can say something more about the eigenvectors and eigenvalues of this matrix given this property. Any vector that is orthogonal to the one